Thank you. So, yeah, so thanks, Ali. Remind me, I should make a advertisement for my university. So it's a new built university in China. And it's my friend, Professor Tian. So we are hiring people. So that's just one advertisement. And so we can start our talk now. So we back to the very beginning of our title of our talk is the method for abelian action and then the centralizer breathing. So we back from the very beginning. So what is the centralizer for diffeomorphism? So I try to make my talk today is very make it like as simple as possible. So if you have any questions, just ask again. So let's make the basic assumption for the talk today. We will always assume F is infinity diffeomorphism on a compact manifold. And then when we talk about the centralizer, so sometimes we mean C1, sometimes we mean C alpha. In general, we mean C infinity centralizer. So definition is simple. It's just a smooth diffeomorphism. Using that. I use C infinity. Sometimes I just use ZF. And then if I write down like Z0F or ZRF, then it just means that I consider here I consider all the homeomorphism commuting with that. And here I consider all the CR diffeomorphism commuting with that. Right. Okay. So you will see here our plan is try to show some examples, very easy examples. And then we ask how centralizer varies, maybe in C1 topology. And then some methods. So that's our plan. Okay. So let's start from the very easy example. Very easy. This identity map. So in this case, we know that the whole group, whole diffeomorphism group is homogeneous. So you can see here we have a very large centralizer. So you can imagine it's like a huge symmetry, and then if you have a large centralizer, then larger centralizer, then have like the preserving like more advanced structure. That's always the intuition. Okay. And then easy exercise is the converse one. Exercise. I will prove that. So the reason is actually very simple. So if we have this so huge centralizer, then you can find the ZF, or I should say for any x such that f(x) not equal to x. So if we can show this set is empty or there's no this x, then we know f is empty. Otherwise, I take arbitrary x such that fx not x. Then I can construct G in centralizer plus the So you can always do this because this group is so huge. This is really an exercise. Then you will get the prediction for you to solve. So this one, so this one not equal to fx by our construction tree, but on the other hand, by commutativity, we get this one, and then gx is just x. So we can get a complete. So this is a good exercise, and in particular, if we know the f acting, so for double dependent on n, so double dependent basically means that for any x1, x2, y1, y2, you can find a G such that G map F to the pair x1 to y1 to the reaction inside and y to y. Okay. I think so far it's okay. Nothing special. And the second example is still very simple, but you will see something different. Rotation on top. So here we basically have like the two cases, you know, from the elementary dynamic systems. So case one, F is not a meaning. So in this case, you can imagine the centralizer is still very big. Or maybe not leave. So people probably basically to find it. So here, that's the case here. So we are all in the case it's pretty large centralizer. Yeah, you can imagine for example, this one or S1, you can so the picture is like this, you basically divide, so you identify one with interval, and then you divide the interval by Q species, and then you can do whatever you want in the fundamental domain. So this single intervals, and then you repeat the same behavior on the rest of the fundamental domain. So you have the flexibility, so that's why you get this back. And that's the easy case. And then the second case is also not difficult. If F is minimum, then maybe I think the easiest proof maybe using for analysis. You don't know this one because all the translations moving there. So here we get a slightly smaller centralizer. The first two cases, so the first two examples we mentioned are extremely large centralizer. That's one infinite dimensional liquid. This one also infinite dimensional liquid. And this one is a finite dimensional liquid. So I just use liquid here. And then an interesting, so we can ask the same question like this. So we ask the conversely. So observe here, our F is just minimum rotation, and then the centralizer is all the translation group. So in particular, in case B, we have that it means that for any point X and Y, take this one element in the F. So we can ask a similar question like that. So in F is minimum and 20. So what we can say for F in the first example, we just take F and then we just assume a centralizer acting on n doubly 20. And then we get F is identity. And here we just assume the F acting on n 20. But we have to assume to inverse. And then the answer is F mostly from the rational rotation. So again, minimal rotation. We will back to this one maybe later or maybe for our last talk, but this one is not acting up very hard. So far it's okay. I mean, even I didn't give proof for this one, but I think the phenomenon is not difficult to understand. And remark, we can answer similar question without minimizer function. But I'm not sure if we have time to discuss this one. We can answer this question. Okay. Without minimizer assumption, we can classify as satisfy this condition. And we may back to this one in the last talk, but not this talk, not the next talk. Okay. So far we have identity map, we have the rotations, and then we go to uniform hyperbolic map. Yeah. Case B. Oh, we can. Oh, no. Oh, sorry. Let's write it down. Damjanović and you. Let's go to the again the easy example for cat map. Okay. So here we have a infinite dimensional V group centralizer, and then for this one the dimension goes to 0. So I should use F. So A is a matrix, so F just means induced act on A of column. I forgot to mention the key definition is the triviality of centralizing. So we say it's trivial. So here we can take out whatever R here if it's equal to only the power to the only the group generated by L. And interesting fact here, F is not a trivial. So the centralizer of F is not trivial, but the virtual trivial. It's just coming from the easy linear algebra fact. This one exists. So we can find the square root of this map. So then this one is like finite extension of Z, finite extension of the power, not only the trivial one. Okay, but it's called virtually trivial. So you can see the word virtually is not a very rare case. I mean, it happens for you even for this very simple case. The square root of the matrix. Square root of the matrix. So it just means the square of this one.
So the virtual trivial became a finite extension of
yeah. So we say is virtually trivial. So is finite index subgroup in and actually we need to prove it. So we say it's from some. I remember Danijela gave already gave the part of the proof. It's coming from some elementary, not elementary, but some fact of the number theory. So coming from the fact like this, fact one in this is algebra fact for any matrix A G L D Z. GL means the determinant is 1 or minus 1. The group in GLDZ. Here we need the key assumption is A is irreducible. Means that the characteristic polynomial is irreducible over Z. So under the irreducible assumption of A, we get a centralizer in this metric group. It's a abelian, finite generated abelian group. And its rank. So then it makes sense to talk about the rank of this group. This one I should write it like there and rank there A equal to R plus D minus 1. Where A has R real random value. C pairs of complex random value. In particular, in this case, we can check this characteristic polynomial for A equal over Z, and then it has two real and a value, the rank by this formula is 1. And another example is the one like Danijela mentioned, the AB example on T3. For that matrix, the rank is 2 because at that time we assume that matrix has 3 real and a value. Okay. I want to say this is only for linear, but now automatic. I should write it down like this one, only in GLTC. And then the second, this only back to one. What? Yeah, sorry. Yes, yes. Yeah. So I didn't provide proof for this fact, but the proof for this fact is, so that's why I say it's not a elementary coming from the table. Okay. Okay. No, I will make it. So this one can be proved by division. Yeah. And this is the fact only in the GLDZ, and then the fact two is the result by I think like 960. It's FM voltage on your manifold. This is on power. Saying that, so if we have a F is an ergodic automorphism. So let me just get a result for power. I should make it out. Ergodic automorphism from power. So no translation here. All about automorphism PD, and then G is the homeomorphism. On PD such that as before here, then G is a prime. Okay. So sorry. Oh, sorry. Thank you. Yes, sorry. No, I think that's right. Yes, sorry. Minus one minus which one? Yes, yeah, yeah. Yeah. Fine, but yeah, yeah. Thanks, yeah. Thanks. So from that fact and this fact, we can think we don't only to verify this fact, we only need to show that does this one provide any automorphism to looking at A. So we only need to know the translation part is finite. So then that's fact three. And then commuting with all F is induced by 101. So should only then there are only finite many choice of this piece. Okay, so the formal proof for this one actually is the combination of these three facts, but I think each one, yeah, in future you need to review. Assuming then this proof is not typical. Yeah, okay. And this one you can do it by hand, by word analysis, at least on Harvard. And this one is, I think it's an exercise. Yeah, not a typical. And that gives us the centralizer for the classical Pac-Man. Yep. Yes, sir. In fact, so here I only assume F is the 211 used by 211, but actually you can replace F by any hyperbolic automorphism. So, yeah. So, maybe it's a proposition only finitely many translations. G satisfies F G equal to G F, and then F is a hyperbolic. I think yes, sir. Where F is hyperbolic. I think actually avoiding hyperbolic automorphism on top. Okay. And then the last example, maybe last example, I would mention it's not a explicit example, but it's a theorem. But Bonatti-Crovisier-Wilkinson. So for C1 generic F, I think you actually prove for Diff 1, but yeah, let's or any Diff R. This C1 generic, this one you can. Yeah, I mean here you can be anything. No? Okay. So then here is the one answer. So we have like 4 classes of examples. The first 2 classes, the centralizer is huge. And then for irrational rotation, the centralizer is finite dimensional loop. And then for hyperbolic automorphism, the centralizer in this case is virtually Z. And then in the example Daniela mentioned in the first 3 lectures, the AV example, that A, on T3, the centralizer is virtually Z2. But they are always discrete, so you get a smaller centralizer. And here is the smallest centralizer, it's trivial. Okay. So you can imagine the picture is like maybe like this. So we start from any diffeomorphism, whose diffeomorphism, and then we consider this is the C1 small pole, C1 small neighborhood of. You can find by this result you can find actually we didn't have. So I write the original one by purple. So by Bonatti-Crovisier-Wilkinson theorem, we can perturb the purple one to get in this form we can get them to make the centralizer to be the smallest one. And on the other hand, by the result for irrational rotation, this is the case perturb and given diffeomorphism to make the F small is possible in the C1 topology. And if we take F0 to be irrational rotation, we can also perturb F0 to make the centralizer become extremely large because it can be approximated by rational rotation. So the problem I think I raised the first level. So the problem how the centralizer varies when you try to perturb the system in C1 topology is quite complicated. You can make it to this one. You can make another row. Actually, this one make it decrease, and this one you can make it decrease. So both are possible. So this problem is kind of complicated. But the good thing is that for Anosov case, for most of them we know the answer. For some classes of them we know the answer. I wish it. Okay. Yeah. Oh, okay. Okay. So for S1, C1, density, ZF is huge, a lot. And then general, yes, and then C1 general. So it's complicated. So I mean, what's the first thing? I think the last the theorem you mentioned is the propel, but I forgot the first author. How to, I don't know how to spell it. Okay. For CR generic. Okay, so thanks. Okay. So we try to answer the question. So how does the F varies? Maybe in C1 topology. So you can see there are already some results here, and then this the answer is not so easy for this problem. And then let's give the result for Anosov case, for some Anosov case. So this is a corollary of the result Daniel mentioned by hyperbolic curves and one. Although they didn't state it, but it's an easy query for their result. So we take A in, let's say, SLDZ. Let's say everything on powers make the world easier. Is so we assume A is irreducible, and F is the diffeomorphism induced by A. Then we get the following classification for centralizer to partially answer this question. I can do it. If so this one this is F0 because it's before the basic. If F is C1 close to A, F0, then we have following dichotomy. The ZF, so then DF is either virtually this, virtually this, virtually the point of F, or virtually that K, and then K is a constant, depends on A is only it's just the rank of it. The rank of the R plus T minus 1 we get from the tertiary unit theorem. So in the case that A, the rank of a centralizer in the GLDZ, the rank greater than 1, then these two cases are different cases. Otherwise, these two are different. The key thing is that if we have this case and then we have it greater than 1, then we know F is the infinity conjugate to F0. Yeah. Yeah, sure. Hyperbolic. Yeah. Otherwise, it's extremely difficult to follow. Thank you. So the proof for this result is kind of simple if we assume the thing by Rutherford and Wang is that okay, if in this case we couldn't say anything, and if we can find some tree using with F and then the linear data or the pi1 data of tree with a matrix and then commuting with A, but not the power of A or not the square root of A, they really generate some deficit. Then at that case, we really get kind of high rank action test. So we need to back to Danijela's talk. And then they show that if you have a Z2 action kind of high rank, and then if you have one Anosov element in Z2, then you get reduced. Here, the C1 close means guarantee that F is on. So that's the only assumption we need C1. So we can see here we can answer this question for under the assumption for under the hyperbolic assumption. Yeah, it should be because I mean the tricky thing is the original result is only stating for T infinity. So we only can I mean for this result if you want to get an easy query for their result, you can only state it for T infinity.
So this is just centralized.
Yes. So far it's okay. nothing deep, right? Because we skip the first deep simplex. You know, we have something deep now, but then you not think too much. If A is hyperbolic but not reducible, I don't know. It may be a math. The structure may be quite complicated, depends on the if A has total block and then depending on the dimension of the B. Actually, I don't know the clear question. And if without the assumption A is hyperbolic, so let's take A is something like generally hyperbolic means that the A is irreducible but some eigen value is no one. Then this problem becomes I think extremely difficult and then it's wide open. We basically what we need to show here we need for the second problem we need I have illustrated that we need a semi-local version and a C1 version of the result by Danijela and the Katok. So yeah, this one is wide open and I keep on. So what's the last one? How to start? FABN. Teacher. I think generally wide open and because in Damjanović Katok, in this case, people consider this direction, but the generators, both generators pose the algebraic one, and then it's not only C1, so the R artificially large. So and then by beautiful proof, the complicated proof, we get a local proof. But here, if you want to ask this question, you want to get so F is equal to F, so we don't know how. So if anyone interested in this one can help later. So we will not say anything for this from the rest of part. Okay. So you can see the partial hyperbolic. This is partial hyperbolic case. The second one is the word becoming super difficult. So maybe let's consider some easier partial hyperbolic case. I will. So again on torus, so everything on torus. So this one is an Anosov times identity. So you can think it's large here. So one as one two and then times. And then we can know that F0 that we can use to the Morgan side. So we have some first again this one too because the identity. So you can show that it's virtually this means virtually. Okay. And the second remark is that even with perturb F, we can still make it a large. Extremely large. Because you can approximate the identity by rational map, so a rational translation. And the third remark is that to recall our picture, that picture. This is F0. We have some by the Bonatti-Crovisier-Wilkinson have a lot of element flow to it, P1 flow to it, and then with the general there will be a trivial centralizer. But among them, there's a good example, famous Wilkinson example. Pathological signification. Okay. So for this case, right? Close F F0 with the trivial distributor. Yeah, this is trivial. Okay. So we will back to this point. Yeah. So for this example, we already said this can be fused, and then by Boston result, can be small. This is like it. So for these two examples, we know that the F is not a body. So maybe we think, okay, maybe we assume a godicity. We can have a good classification for centralizer. So that's the one proof I would like to say more thing. So let's simplify the function. So I'm saying that the Wilkinson example has virtually trivial centralizer. Yeah. And I will show it to you. I consider F close to F0, P1 close to F0, both disturbing. And I can assume it's ergodic, but maybe the proof makes it a little bit complicated. So for simplicity, I assume it's successful. And we will see later, maybe the one frequency also can be removed. And then I want to show that here F have two cases, either D or virtually D. Or for T. And then in the second case, F is smoothly conjugate to an isometric extension or rotating extension. So to the case F Y maps to some F Q type X. This is the Anosov map, and then Y plus smoothly conjugate to something else. So that's the second case. You can see some integrity, and this one is that small, pretty small, virtually small is And I just say this baby case in our group. It will use with the map like this. Constant theta. So this will provide T1 here. And the original the equation will provide the Diff. This is a one example. Yeah, that's no rigidity, and then we will show the rigidity, the strongest rigidity one next part. So today we show a rank one result. There's some confusion for this one. So the step one is very easy. Oh, sorry, it's a very classical. So people already know this. Not easy at all. Classical. There exists compact vibration, compact interpolation, F event, and such that we have this topological vibration. And this one, in this case, topologically restricted. And this is pi, and this vibration is fibered by the W. This is not. And okay, so we have step two now. That's a key thing actually, and then it's not a quite trivial. So anything in the centralizer is also preserving this vibration structure. So the non-trivial things here, central population may not be uniquely independent. Uniquely independent. So I mean the naive guess, okay, this one is some population tangent to EC, and then it's F invariant, so it should be WCF now because it's not that after there's no uniqueness of the left hand side. So this one can be proved. I only get a little sketch. Oh, I have 10 seconds. Okay. So maybe leave it to the next part. And I think this one in general is open. So you can ask the question like, if you have partial hyperbolic diffeomorphism with the integral centralization, and then you pick something in the centralizer, YG is the WCF. That's, I think in general is open. And then we get the key step, step 3. So step 3 just coming from step 2. So we just show that any G in centralizer preserving this vibration structure. In particular, well, F, we have a cumulative diagram from this vibration structure like this. And then we call the induced map, the portion map by F bar. Then G, we can also replace F by G here because we have step 2. So G bar is also well defined for any G in the centralizer. Okay, so we have a map from centralizer to formula this topological space, topological isomorphic to solid map of G. This is a group homomorphism, you can imagine. And so we get kind of short exact sequence. So we wonder what is the kernel for this map. I use this is a projection, so I use P for example. So we get the kernel of P, and then we get the F, and then this one goes by P goes to one. So I should make that like this. So we have. So this one is not a projection map. Right? It's not a piece. It's not suggestion, but it's like build it. So we have this kind of exact sequence, and then the kernel P has the dynamical meaning. There's all the map fixed in the center. For any x, we have G, W, C, F, X. So not only preserve information, but fixed scenario. Okay. So to understand the group structure or what happened for this one, we basically need to know what happened for kernel P, and then we use the notation CZF, means center fixing for F. And this one is the image of P for this one. So you can imagine to understand ZF, we basically only need to understand what happened here and what happened here. For this one, because the key thing is the image of P commuting with the S bar, and S bar topologically is just 2111. And then we know for 2111 by our discussion for Anosov automorphism, any C0 map commuting with it is a prime. So this group, image of P is virtually Z. So if we want to show our results here, we basically only need to know what is CZF. So yeah, maybe I just get P and we leave the whole group next part. So the easiest way to do it is by either two Wilkinson and then the Danijela-Wilkinson. So the second paper for the dichotomy for center disintegration. So basically the center disintegration is either atomic or we have the F is smoothly conjugated from like this. Because in the second case, the active statement is for Lebesgue integration, and then by some work, we can show this one smoothly conjugate to position. So the only thing is, if we have this one, can we show that CZF is finite? And yeah, I don't have an idea. It's very simple because for anything in the centralizer, you need to preserve the atoms for almost every point or almost every bit. If you preserve the atoms, and then you can only use in the atoms. So you can only have finite forces of your centralizer in almost every. I will give more details next time.
So just before to open for questions, I would like to remember you that today the launch is 12 and 40, and the bus leaves 13:30. Okay, so comments, questions?
Yeah, but for the to be larger, but for the this very special law that is going to say, we know first the Anosov homomorphism we consider topologically conjugate to 111. Yeah. So the problem for 111, then it's not.
Or questions? No, so let's thank our speaker again. We come back in 20 minutes.